So let's go now to protocols. And I will show you where you will find those elements, starting with the classical transport layer protocols in the internet. Classical because they exist since the early 80s, first ideas of TCP back in 1974, so quite old. Okay, so application layer, talked about application layer protocols, HTTP and DNS, SMTP, etc. They use the transport protocols as communication service, and the most prominent are the TCP and UDP, and quite often we also talk about the TCP/IP protocol family. So, because the TCP and IP, they're really married, I mean, as we will see. There are some more. So, you see here now layer 3, layer 5 protocols, and we also talked about host to network layer, Ethernet, etc. And here we'll focus first on TCP and on UDP, the classical protocol. And later on, I will also cover multipath TCP and QUIC. There are some others. Well, they had their time, like the SCTP used. Yes, DCCP never really took off. There are many, many, many more, but these are the most prominent ones. So SCTP used in mobile communication, for example. And as I said, QUIC and multipath TCP I will cover later. You also see that there are different protocols for connection-oriented services, like TCP, typically used by SMTP, by HTTP. And for connectionless services, we typically use UDP. DNS, for example, can use UDP. But we know we can also use DNS over HTTP, etc. QUIC itself uses UDP. I'll handle this later. Okay, so these are the transport layer protocols, but first of all, let's start with UDP. UDP, very simple. UDP is published in 1980. John Postel was the one creating this. And the idea is, keep it simple, stupid. So it's only a 3-page standard. That's ultra short. Small header. It's connectionless, unreliable, like IP. So why do we use it? Well, we'll come back. So little reliability, but it's fast because it's very lightweight. So there's no acknowledgement between the peers. So if the packets are incorrect, okay, discard them. So there is some basic checksum, so you can detect corruption of packets, but duplication, sequence order permutation, packet loss, all possible. So, well, if an application needs in-order delivery or this, then don't use UDP. If you need reliability, well, then do it on your own. So then you can create application layer acknowledgements and retransmission. So how does the header look like? Most important, source port and destination port. This is the main motivation for UDP. We need the ports for multiplexing and demultiplexing, so we address the application by the port numbers. So port numbers, source, destination ports. That's the important part. Then we have a length field, so that's the total length of the datagram, header plus data, 32-bit words. And we have an optional checksum. So why a checksum? I mean, IP doesn't have a checksum. So remember, so we have the IP layer 3 header somewhere here, but we have here on the link layer, we have a checksum. So there's a checksum, and the checksum will be here at the end. So frame check sequence, CRC here, and this CRC will protect everything. So why checksumming it again? This CRC is generated link by link. So checksumming here, well, there's discussion, maybe useful if someone in between a router changes something, then the checksum could detect an error. But this checksum is not useful for detecting errors during transmission. This is handled by layer 2 checksum. How the checksum is calculated, I will come back when I discuss TCP. And then we have the data, the payload, and payload field. So why using UDP? Well, multiplexing. So we need this multiplexing because we need our socket pair for communication. That's the socket pair, 2 sockets. So why using UDP? Well, it's good for real-time communication, voice over IP, video games, etc. So UDP sends the data immediately. So there's no buffering, things TCP does. So same thing on the receiving side. As soon as you receive a UDP packet, you immediately deliver it to the application. So there's also no connection establishment. It's very simple. We have no states, no connection state, very small packet header. Plus, if you do multicast, typically you use UDP. You cannot do this with TCP. So UDP, very simple, and some applications use it. So for network management, we learned SNMP uses it, DHCP uses it, the classical DNS uses it. Reliability is not an issue. Well, we simply repeat a request. So many more things use it. Network file systems, for example, because the performance is higher and we don't have any big issues. We typically are on the same physical network servers and clients. UDP was also used for streaming, but more and more streaming platforms switched over to TCP. Also some voice over IP, also proprietary application protocols, they quite often use UDP. Well, that's all about UDP. So UDP is not really complicated, but remember, we need it mainly for multiplexing, demultiplexing, and later, as we will see, for QUIC, new protocol. So let's have a look at TCP. That's way more complex. Again, an overview. So TCP was first published in 1981, so a year later compared to UDP, but the first idea were there already in 74. Many RFCs complemented this original specification, obsoleted the specification, and the current RFC is 92-93 and containing many new things. It's a point-to-point protocol. We have one sender, one receiver. But no matter who established the connection, it's a full duplex connection. So if one side established the connection and is a sender, and the other side is the receiver, this receiver can also be the sender. So it's bidirectional flow in one connection. There's no unidirectional flow in TCP. Okay, we will learn that TCP works a lot with buffers, send buffers, receive buffers, and we always have to think our data is a stream of bytes, a byte stream, and TCP will, for practical reasons, split this into segments, and there's also maximum segment size, for example, 64 kilobyte. The idea is that the application can, if the application wants, continuously write data into a TCP buffer. So maybe a single byte, a single character, or maybe a larger chunk, that doesn't matter. And then TCP will decide when and how it creates a segment and transfers it to the other side. And then another application can read out the buffer. TCP is connection-oriented, has this handshaking, you initiate the connection before you exchange data. It's reliable delivery, it's in-order delivery, and it has a flow control, so the sender will not overwhelm the receiver. Plus it has a congestion control. So the congestion is auto controlled, so the receiver at least tries not to overwhelm the network. It's pipelined. We will see that we use sliding window mechanisms to control this congestion and flow with the help of certain window size with also a limited quality of service. Well, yes. So TCP accepts a stream of bytes, but will segment them. So TCP operates, yes, on segment, and that's important for the connection establishment, also for window size, transmitting data, sending confirmation, etc. So these are segments. We can also talk about packets, but typically it's called a segment here. But it's a packet on layer 4. We'll learn that there are some urgent messages or urgent packets, and they are outside the normal flow control. The application sees sockets, again our socket pair, sockets on the receiver and the sender side, and identified by our IP address and port. As in UDP, so that's the classical situation that you have your client using your socket. That's our service access point for layer 4, our transport layer. Then we have the IP address or access point for layer 3, the network layer. So, and if we have here our layer 3 packet coming in, we need our ports to demultiplex to find then the right process, server process, that can then handle our data. And servers typically wait at well-known ports, like for example, if this is our web server, the web server here waits at port 80. Waits all the time until there's a connection request packet for port 80, and then all the connection setup starts, as I will show you. There are many applications using TCP, like classical file transfer, FTP, you see low port numbers, old protocols. HTTP, BGP, our routing protocol, sets up connections between the routers, those peers, SMTP, mail, etc. First TCP concepts, as I said, back in 1974, and Win Cerf and Bob Kahn, they were the fathers of TCP, and many others were involved. But those are two names to mention in the context of TCP. And yes, TCP, we will see what the future brings. I mean, more and more protocols go now to TCP, they use UDP, but also other protocols like HTTP, so we'll see they use QUIC, other protocols, and also TCP changes over time, as we will see. Please check out, there are many transport layer protocols. So, and you can also try to find out which are still in use, declining, upcoming. So, well, TCP is there since many, many years. We don't know what the future will bring if we still use TCP 10, 15 years from now. I think yes, but maybe not for the web, maybe for some other purposes. UDP, very simple, 3-page standard. So why is it still needed? This is just IP on layer 4. Yes, you can use raw IP, but UDP adds something. What is it? TCP tries to solve many issues. Just think, name a few. What is TCP solving? What IP doesn't offer? And then I will come back to this many times. What does this mean? TCP is byte stream oriented. We send packets called segments in this context. So segments here, these are our packets in TCP speak, but TCP itself is byte stream oriented. What could this mean?